All right, so let's get started. Hopefully, the recording system will work today. You have been talking since you got in class, and now you have questions. So page 47. So the exam one probably will be after the next homework. Okay? So 47. So this will be, what is today? February 8th. And I think this should be then lecture, is it 8? Lecture 8, okay. Okay, so it's Thursday, so I don't want to start anything new on the theory. Yeah, but let's do. Okay. Last time we did one example about to learn how to use a table. Was it clear, or do you want to do another example? You want to do another example? I mean, interpolation, I've done it once. From now on, you need to learn. I mean, we can look at interpolation, but interpolation is calculus 1. Okay? I don't say that to make you feel bad, but it's calculus 1, no? All right? We can do another one, but I'm not going to be doing interpolation all the time. I did it once, so I can show you, but maybe we might do it again once more today. So what was the problem number we did last time? Let's just do a new problem. 331. Okay, since I'm here at the problems, I was looking now different problems. So let's do one in the area of 331, I'm guessing, with tables. So 331. But I don't know if we're gonna have to do. So you pick. You want to do 332 or 333? $336. Which one would that be? I don't know. 334.
Like they give the work as a minus number. Is that because they're going by the textbook
Yeah.
equation?
Yeah. So you want to do this one? So we can look at that. All right. So let's do 332. Okay. So let's see if this would work. If I eliminate this side over here, maybe I can minimize this. Do something like this. That's not gonna work. I know, what I'm trying to do is to put the two things over here. And now I can maybe change the zoom level. Let's see, 5. Can you kind of read over here? I can go maybe 100. Is that good or? Good for 332? Can you read it? I'm just trying to put it here because that way, as I read it, I mean, I can probably do it a bit bigger. Let's see, 125, 115. Okay, I want to be able to read everything. All right. So let's do another example. So let's do 332, or we can do another one. I mean, because 332 should be fine. Okay, guys, so remember, this is part of the solution, okay? So 332, we know 7 pounds of propane in a piston cylinder assembly. All right, so the first thing I do, I do my piston cylinder assembly, okay? So now, since I've done this, we know we are dealing with a closed system, no? All right? So what else do we know? There is 7 pounds of the substance, and the substance is propane. Okay, so initially, so we have P1 is equals to 200 lbf inch square, and the initial temperature is 200 degrees Fahrenheit. So undergoes a constant pressure process to a final state. So I'm guessing final state will be 2, no? So, all right. State 1. So I call my final state 2. I know this. I know it's a constant pressure to a final state. The work of the process is minus 88.84. Okay, so I think that's why we're doing this problem. So remember, the sign convention for the textbook is different than the one we have in the class notes. Okay, so for us, heat and work going into the systems are what? Positive, and the ones come out are negative, no? Okay, so over here, for the textbook, what is it? It's the same sign convention for the heat. So heat going in is positive, heat going out is negative, but it's reversed for the work, no? So if in the textbook they tell you that the work is negative, what does that mean? Is that heat going into the system, or is that work going into the system, or is that work coming out of the system? So it's work done on the system, is not work done by the system. So here, imagine, it's not a problem, but imagine that you have some type of little fan, okay? Whatever, so you can put work into this, and the amount of work going in through the fan is 88.84 BTU. Okay? So let's see, at the final state, at 2, determine the temperature in Fahrenheit. So we need to determine T2 in Fahrenheit if the process if superheated, okay, or quality if saturated, okay, or what is the quality? Is the letter X if mixture, I guess they mean here, because if we saturate it, it's going to be 1. Yes?
So if we're going to say that work is positive, will we ever in the textbook get a positive work value?
Yes, if it's positive, then it's work done by the system.
So that if we're going to do the other side,
Yep. Yeah. All right, so any question? Do you all understand the problem? What needs to be solved? Okay? So remember, in order to use the tables, what do we need to know? What was the first thing we put on the class notes last time? Is that we need to determine what is the state of the substance. Because if you don't know what is the state of the substance, we don't know which tables to go look for the appropriate data, no? Okay? So let's start by that. And I always say that generally you're always going to have to do one of those figures, no? So if we have a constant pressure, which figure do you think is going to be easier to do? Remember, we have the choice between, they both look the same this way, but then one had lines of constant pressure, the other one lines of constant temperature. So since we're dealing with a piston, generally it's easier to work with lines of constant pressure. So let's say, so I don't know what's going to happen. Okay, so line of constant pressure. So let's say we are here. Again, I don't know if this is, if it's going to go up or down, but so this is a line of constant pressure. So here we could write P1 equals P2 equal, let's say, to 200. Okay, I think I can remove this now. We might need to go to the tables, but for now, I think we can remove it. Okay? Unless you want it there, it's not a big deal, but. Okay, so if this is the line of constant pressure, here what do we have? V, and over here, what do we have over here then? Temperature. Okay, so in order to determine the states, we always need to know two different properties. If we only know one, if you only know one point here, let's say around V, you don't know where to go around T, no? In order to find a point on a plane, which is this one, no? This figure, you need to have two properties, no? The X and the Y, okay? So in this case, we know what is P, so we need to know what is T, no? So for example, if T is under this value, it will be what? Liquid, no? If T is higher than this value, then it will be in this area, will be gas, no? All right? So let's see. So we need to go to the tables for the propane in English units and look at what happened at 200 pound-force per inch squared. All right? So here we have to open this over here. So I'm not going to be able to do this way or not, but let's say tables. These are, oops. Okay, AE. So let's see, propane looks like here. I'm guessing it's A16E. So probably we're gonna have to go A17E, I'm guessing, because generally they give first the one of the temperature, then the ones of the pressure. So which one am I going here? A4. A12. A18, I went too far. Okay, so I'm probably gonna have to do this bigger. I'm probably gonna have to open it. Okay, so here we are A16 for propane. So the first table will give you in function of the temperature, no? We could still use this one, but it's gonna be a lot difficult. Well, not a lot difficult, but you have to come here, do the interpolation and so on. So let's go to A17A. We know the pressure, we are lucky to give it in pound-force inch squared. We go to 200. Okay, what is the temperature, the saturation temperature? 104.6, no? So that will mean what? What would be our state? So basically, we know that the temperature over here is, the saturation is 104.6, no? But what is T1 equal to? 200. So let's say, 200, let's say 200 is over here. So we do this. So let's look at the data. So we went to table. A17E, and we look at P equals 200. We had that T was equal to 104.6. Okay? So since this value is higher than the 104.6, the state 1 is what? Gas or superheated, no? So state 1, can put gas or superheated, whatever you want. All right, so we know this. So now that we know this, okay, so now that we know this, something we could do is, I think we're going to need it later, so let's just do it now. We can go to the appropriate table and let's say find the value for V1, no? Okay? So let's say, oops. All right, so let us say 48. So now, gas, so what table we need to go? probably is going to be the following one, no? A18E, which is should be superheated propane. So superheated propane vapor, we go to this table. We go to table A18E, and here we need to go to the pressure of 200. When you look at the table, 200 over here, and what is the temperature? 200, so we don't have to interpolate. So we are lucky. So if we look at this table, what should be the value? For V, 0.7025. Again, I don't say that for anything, but I think I mentioned to you multiple times. Studying is like, well, not 100%, but kind of similar to sport, no? I always give the example about free shots, no? There's nothing complicated to understand, but what's gonna happen if you don't practice? You're not gonna make it, no? Using the tables is the same, okay? Because I see a lot of people just looking at me and this. Guarantee that the day you're gonna have to do it on your own might lead you to a disaster, okay? So I do it with you in class to practice. So it would be good if you come with the tables. Okay? Because when I do it, it might look easy, but it's not as easy as you think when you don't have the practice. Okay? It's like you look at the top athletes on TV and you say, oh, that's not that difficult. No? I can do that. But then what happens when you go and try to do it? It's not the same, okay? So same thing with studying, okay? All right. So over here, we say that because it's on the gas state, we go to table A18E, and here we need two values. So at P equals 200 and T equals 200, what do we have? V1 was equal to 0.7025, no? Okay? And if I'm correct, the units for this should be cubic feet per pound. Yes?
Why did you use T equals 200?
Because this is what is given to us in the problem. We know at state 1, pressure is 200 and the temperature is 200. Okay? All right. So in order to find something, we always need to have two different properties, no? So over here at state 2, we only have one. So we need to find another one. So what can we use in order to find another property over here? Probably we can use the work, no? Because what do we know? We know that this process, because it's within a piece of in the assembly, is a constant pressure. All right? So if you want, we can say, what is the work? It's minus P dV. Okay? If you want, I give detailed calculations for now. What is specific volume? Volume divided by mass. Specific always means per unit mass, no? So from here we can get that volume equals specific volume times mass. Okay? So I think if I come to this one, you get work equal to minus P. M is constant, so I could put it PM dV, no? Or I could just write, oh, it doesn't matter because we have the mass over here. Oh, so we could do it that way. It's fine. So we are good. I was trying to do everything per unit mass, but it's fine. So if P is constant, so for constant pressure, what do we have? Correct, will be this, no? So we have at the end, this will be equal to minus M times P times what? V2 minus V1, no, for constant pressure. All right? So let me just rewrite this a little bit differently. So this will give you what? Yeah, so basically I'm going to have this of minus P V2 minus V1. So over here, what is the only unknown? V2. So can we solve for V2? So multiply in your head by minus 1 on both sides, and this should give you what? V2 will be equals to what? V1. So this becomes negative minus yeah. I mean, if you want, let's do the middle step, okay? Yeah, I think that's correct, okay? Just move this one over here down, so you have minus V2 will be plus V1, and then you start changing the signs. All right, so we have this expression over here. Okay, so here, all right, let's look a bit at the units. So V1 is given in what? Cubic feet per LP, all right? So we know M is 7, is in pounds. What about the pressure? Pressure is given to us in pounds-4 per inch square, no? So I have a problem over there already with the units of length. Let's see what is the work. So the work over here is given to us in what units? In BTUs. So what is the transformation from BTUs to the English units? I think that's the one that's like 700 something, 778.
Yeah, 778.17.
778.17, and I think this should be foot pound force. Is that correct? All right, so foot pound force. So what does that mean? It's better if we change the units of the pressure to what? So far we have P equals to 200 lbf inch square. Yeah? So we want to eliminate this, we want to transform the inches. What do we know? 1 foot is how many inches? 12. So now if you do the square, 12 square is the 144, no? You take the square of everything. So if you do this, what do you get for the pressure? So it will be 144, so 28.8, 10 to the 3. Yep, 10 to the 3. And what should be the units for this? So here we'll have, this will cancel, this will cancel. lbf foot square, no? Okay, so now let's go back and substitute into this equation over here, into V2. All right, so we're going to have V2. Let me rewrite it again. V1 minus work divided by M times P. So let's see if I can make it fit over here. So what is V1? 0.7025. Okay, so now put the units if you want. I don't know if I'm gonna have space, but cubic feet per pound plus. So let's see, what do we have? 28.8 10 to the 3 LBF divided by square foot. Maybe I can zoom in a little bit if that helps. Does that help a little bit, or is it a minus? Yeah, minus. Oh, that was the pressure, correct. So you see, I knew I was going to do something wrong here. So what about just go to the next page, okay? And if you want, just remove this, and I'm just going to rewrite it on the next page. Okay, so the equation was V2 equals to V1 minus the work divided by MP. So now, so this is equal to 0.7025 cubic feet pound minus, and you're right, I was doing the wrong value, the work is 88.84. Oh, we shall do that transformation. So minus 88.84 BTUs.
Isn't the work negative?
The work, okay, be careful here. The work is what? We already took into consideration the sign of the work when we did the plot over here, no?
Oh, yes. Oh, yes, yes.
So BTU, so we need to be careful here. Maybe I shown it before again. So what do we know now about, let me, I don't know how I'm gonna make to fit everything. Then the mass is what? 7 pounds. And the P was the one I wrote before, no? The 28.8. 10 to the 3 LBF foot square. But what do we need to do with the BTUs? So we know that 1 BTU is what? 778.17 foot LBF. So let's see what happened with the units. So obviously this BTU will cancel with this BTU. This pound force will cancel with this pound force. This pound is going to stay, and this foot over here becomes cubic foot with this square foot down there, no? So what do you get for V2?
1356, 1360.
Can somebody double check? Again, same thing with the calculations.
Did you just convert the units of the
So point. So 0.3, we all agree with that, no?
Yeah.
Then is the other two digits. 0.3 what then? 359.
I got 775. I got 359. 349.
349. Okay, guys, you see, we already have like 3 or 4 different answers by people doing the same calculation. So the same, you see, applying calculators can also lead to different results. It's practice. So I don't know, let's say 3, so 36, 359. I heard 2 people saying 359. But I mean, this is not my responsibility, okay? These calculations is yours. So don't tell me then is something wrong. So 359. So this should be what? Cubic feet per lb. All right. Okay. So now if we come to this figure, again. All right, we found that V1 was equal to what? So V1 is here 0.7025, no? So we know that V2 is actually to the left of this one, no? So it could be here, or it could be here, or it could be somewhere over here, no? So how can we find out where it is? I'm going to find out in which state it is. Can we know this value and this value? What do we know about this value over here and this value over here? Yeah, but this one will be V sub what? V sub, what do they have? So I think this one they will call it V sub liquid, no? And this one was V sub G? V sub gas, no? So do we know these values? We can find them from the table we used initially, no? So we can find this value and this value from table A17E, I think. So we go back to table, so from table A17E, at P equals 200, we're gonna have V, I think it's V liquid and V gas. So let's see. So there we go, table A17E. You look at here is the pressure on the left hand side. So we look at 200. So where are the V? So this will be V sub fluid, V sub, so it's sub F instead of sub L, okay? So V sub F and V sub G will be equal to, so let me write it down. So V sub F instead of V sub L is equal to 0.03432, and the other one is 0.5261. Okay, so what do we know? So V2 is between those two values, no? So between V fluid and V gas. So state 2 is what? State 2 is going to be a mixture. So that means that our state 2 is going to be, I mean, I just do it by convenience in the middle because it gives me more space, but let's say our state 2 will be, if this is 1 over here, our state 2, let's say, will be somewhere over here, no? Yeah? So the process 1, 2 is what? We're going through this line over here up to this point, and over here we know V2. Okay? So the problem is asking for what? So if T2 was in this area, they wanted to know what was the temperature. If point 2 was in the mixer area, they want to find what? The quality factor. So what was the quality factor? Quality factor is the amount of gas within the mixture. Okay? So, so using the equation, we have V2 will be equal to what? V plus something X V G minus V fluid. So I think this one is V fluid here. Is that correct?
Yes.
On the page I gave you? Alright, that equation is the one that was on that page, remember, with the two figures? You can use that one. So, now in that equation, what is the only unknown? X, no? If you want here, x2. So we could solve for x2 will be equal to what? V2 minus V fluid divided by V gas minus V fluid. So if we do the numerical application, we get that x2 will be equal to what? So V2 0.359, that's the value you gave me, minus 0.03432 divided by 0.5261 minus 0.03432. So you get 0.662. Can somebody double check? Okay. So this is the same as saying 66.202. Is it 02 or? Oh, okay, so let's just do this, okay? 0.66. Alright? So will be then 66%. Okay, guys, so again, I always say these problems, I mean, if you understand this figure and you use the figure to solve the problem, they are not that complicated, okay? If you try to solve the problem without a figure, it's impossible, okay? So the most important part is to do this page over here. This is the most important page. Okay? This is the page which is going to help you to solve the problem. Okay. So page 50. So let's see, I'm just trying to see what we're doing next. I'm not really following this, but all right, it doesn't matter. Let's keep going in another direction. All right, so over here, we're going to do something. So we're going to write down recalling the first principle of thermodynamics equation, which is what? Equal to the change in energy, okay? Where, let's do summary, where this one was equal to change in kinetic energy plus change in potential energy plus change in internal energy. Okay, so now we're going to say neglecting kinetic energy and potential energy. What do we have? We have Q plus work equals, to change in internal energy. Yes?
Why is kinetic energy?
I mean, yes. I mean, basically, if you think about just the piston cylinder assembly, everything. Okay, that's a very good question. So, for example, you agree that, let's say, to go from let's keep taking the water as the example. When you go from liquid water to, let's say, gas, okay, you can make that process to go very quick or to go a little bit slower, no? You can apply the heat very quick, then it will evaporate very quick, or you could apply the heat very slow, or it will still evaporate, but it will take a long time, no? So in this class, are we taking into consideration the speed at which the process is happening to go from one state to the other, okay? So so one assumption that is taken all the time is the one that is called the quasi-static assumption, which says that you say that the process happens very slowly and in little steps, no? Okay? So using that assumption, what does that mean then? Is that, yeah, but I mean, basically, if we go back, what was the initial equation? We derive everything. Summation of forces equals to MA, no? If it happens very slowly, quasi-static assumption, that means that at the end, what are we really doing? Summation of forces equal to 0, no? Instead of A. So if you go, the velocities is very slow, you can assume that the change in energy, in kinetic energy would be 0, okay? And the one in potential is not that the piston cylinder is going to go up 20 feet, no? It's just going to be very little changes. That's from with the assumption. Okay? Okay. So now, from here, so from Gay-Lussac experiment, which basically So the experiment is say it has some type of box which is insulated. And I think inside there is some type of water tank. Okay, so let's say water. And here it has some type of thermometer, so you can measure the temperature. And now let's say you apply some type of heat to the system. Okay, so if this is insulated in this system, do we have any amount of work? Is there any work being done on the system or done by the system over here? No. So for this problem over here, okay, we'll have what? Work is 0, no? So from that equation, so knowing that the work is 0, what do we know? So let me just write it. So this is 0. So that we have, oops, don't do the dot on top, okay? Just heat equals to work. And what he found out is that the amount of heat that is put into this water over here provided is going to be equal to, obviously, to the mass of the water time a certain constant, which is called over here CV, times the difference in temperature. Okay? So let me just rewrite over here. I'm going to write the same line but without the little mistake. So Q equal to the work here would be equal to M CV T2 minus T1 sorry, I mean, why didn't you stop me here? I wrote something completely wrong. You see, and equal to the change in internal energy equal to the change in internal energy equal to mCV T2 minus T1. Where C sub V is the specific heat, what is known at what? Constant volume. Okay, so let me go to the next page. So here I'm going to rewrite the same thing again, but you know, repetition is the way of learning as well. So here what I want you to remember is what? Is that the change in internal energy is equal to M CV T2 minus T1 equals to M CV delta T. Okay? Or so this is a capital U, or you could say what? Capital U divided by M. This will be equal to what? So this is capital. This will be so uppercase, lowercase if you want. U, okay, will be equal to what? CV delta T, no? Where this U over here will be the specific internal energy. So really, what I want you to remember is this. So I'm going to write it once more, you know. Change in internal energy equal to mCV delta T. Okay? Yes.
That applies to all the, doesn't matter if it's like isobaric or isochoric, delta U will still be the same.
That's applied so far for everything that, yeah, that apply. That equation is general, but if you ask me to remember something, that equation you will be the one using for closed systems. Okay? Okay? So the important thing over here is that Gillisack experiment, what it gave us is that saying that the internal energy, you can rewrite the internal energy in function of a constant, which is CV times delta T. Okay? If you look into more complicated explanation about what is CV, CV is the derivative of the internal energy, the partial derivative of the internal energy with respect to the temperature at constant volume. So what does that mean, no? Okay, so if you want, I can show you very quick. If you want, we can write it down. I think it's the way I did it in some old class notes. So over here, what's this? Oh, it's good. So you see, that was the experiment of Gillisack. I think it was, two S's instead of one. You see, I simplify all that stuff. Okay, so, okay, it is. So you see over here, what is the du? So if you say the property is the internal energy in function of temperature and volume, okay, you take the partial derivatives, no? So now you have that this is equal delta U delta T. If you have a constant volume, what would be dV? 0, no? For constant volume. So at the end you have that the change in heat is equal to delta U delta T at constant V dt, and this is what is known as CV. Okay? If you ask me, all this comes from the partial derivatives. No, but it's not physical meaning. I'd rather give you the explanation from the experiment. Okay? But if you want, I'll give you this definition here, and then we can go through the book. Okay. All right, so let's write over here. Okay, let me just write over here. CV is also equal to the partial derivative of U with respect to T at constant volume, okay? This is not important for this class, but if you go to a higher class, it's from the Maxwell constant, you get them all the same way, okay? Which is by taking the partial derivatives. All right, so now, since we have time, let's go for a deeper understanding. So, let's just restart again from 0. So, Recalling first principle of thermodynamics and neglecting kinetic energy and potential energy. We have Q plus work equal to change in internal energy. So now, if instead of having a closed system, like the Gillow cycle, let's say a closed box, we have a closed system which is a piston cylinder assembly, what would be the work equal to? Minus PDV, no? Okay, here let me just rewrite it as under this form, okay? So if I do this, what do I have? Q minus PDV equal to du, and let's say this is more or less equal to du. So we have that the heat will be equal to what? du plus PDV. Okay? So this is not the final equation, but let's see. Okay. You have a question? Oh, yeah, go ahead. Okay, what happened to the integration sign is this. Let me do it here on the side if you want. Okay? I decided in this class to use this notation over here, no? But really, what should be the general form of writing down this equation should be what? This is all the amount of heat, which is at the end transfer, no? And this is a change in internal energy. But really what happened is that you cannot have the full energy equal to a change, no? So the real equation, the way it should be written, but I didn't want it to overload the nomenclature, should be like a little variation in heat plus a little variation in work, then is equal to the change in energy. Okay? So what happens is that the real equation is that delta W is equal to minus PDV, which then will give you work equals to what? Minus PDV. But, didn't want it to overcomplicate the notation. Does that answer the question? Okay. All right. So now, there's different ways to do this, but let's say, let us consider H, I call it H, being equal to U plus PV. Okay? All right? So now, PV, pressure times volume. So now, I keep this one over here. Okay? And let's call this equation here star. So now, if I do the derivative of dH, what would that be equal to? What is the derivative of uv? Is u prime v times uv prime, no? So the derivative of this would be equal to what? du plus p dv plus v dp. So now I could come here and say du will be equal to what? dH minus p dv minus v dp. Yeah? Now, if I substitute this one into this one over here, so substituting du into the equation star, what are you gonna get? Q equals to dH minus p dv minus v dp plus PDV, no? So this one will cancel this one, and this is going to give us the Q. What did I do here? Yeah, that's what I'm thinking here. Is what did I do here? Du. No, this is correct here, no?
Oh, yes.
Okay, so du equals dH minus v dp. Okay, so all this stuff is correct here. Thing is that I don't want to write down conclusion that is not 100% clear. Okay, so again, over here, when we did this one, we said we're going to rewrite this for what type of system? For a closed system, but we said this time, consider that you're working with a piston cylinder, no? Yeah? Okay. So what happened in the piston cylinder assembly? So in this one, pressure is constant, correct? So if the pressure is constant, what will be dP? 0, no? There's no change in pressure. So at the end we have over here that Q equals to dH, and this one is going to be equal to M C sub P T2 minus T1, or if you want to write over here is that dH is equal to M Cp delta T. Or dH equals to Cp delta T, where little h equal to capital H over M. Where Cp is what? Specific heat at constant pressure, okay, and H over here, U plus PV, is what is known as the enthalpy, okay, and little h equal to lowercase u plus p specific volume is what? Is the specific enthalpy. Okay, so over here what I want you to remember is what? Is that the enthalpy H will be equal to Cp delta T. Okay? Internal energy delta U will be equal to what? Cv delta T. Okay? So all this is correct, okay? But you will see later on, I will tell you. If you deal with closed systems, everything we are doing now, always use delta U, because you remember that delta U is equal to Cv delta T. Okay? If you deal with what is known open system or control volume systems, I will tell you, remember just to use enthalpy. Okay? Which is Cp delta T. But actually, you can also use enthalpy for closed system. So let's see, if you look at the two equations, this one over here, oops, you cannot see it, so this one over here that we use, so we have this one over here, the one we used initially, and then, I have to do this, and this one over here, okay? This one over here. So Q, here Q equal to delta U, equals Cv dt, here Q equals du plus Pv. So what is the difference between using U and H? What does the H include that the U does not include? Yeah, but what is this term? Is the work. Okay? Is the work done by what? Is the work done by the pressure. Okay? Constant pressure within the piston cylinder assembly. Okay? So, for example, in some problems, they will ask you to find what is the work done in the system? I think it's easier if we do a problem, but what is the problem do on the system? So generally you will say, I know the work done by the pressure is minus PdV, so you write this expression, and it can be polytropic, no polytropic, whatever, no? You write this expression, you write what is the delta U, and you can find what is the Q. Okay? That would be the way I would tell you to do it. But if you really understand what you're doing, do you really will have to calculate what is the work if you are using the tables? Okay. All this stuff I'm saying this because of this. If you go to the tables, you see you have values for U over here and values for H, no? So these values for U over here will only include the work done by, the change in internal energy. Okay? The values of H will include what? The values of H will be it's not what I wanted, will be the change in internal energy plus what? Plus the work done by the pressure, no? Yeah? So that's what you need really to understand is that I'd rather you just use the internal energy and then calculate the work using the general expression. Okay? But if you want it from the tables, the H already includes the internal energy plus the work done by the pressure. Okay? So we stop over here. I'm going to try, I'm going to give you for next week, I'm going to create a new homework. I'm going to start putting problems in the homework. Okay? I don't know when it will be due, but if I was you, I would start working on the homework this weekend. Okay? So I will look for problems that cover what we did last time about using the tables.